All right, guys. I'm going to try to go through this as quickly as possible. So as you're going through this and sharing it onto the TV, please make sure to stop it where necessary if you're trying to copy down a graph or just the work. Because, again, I'm going to try to make this kind of a shorter video so that way you can just pause it or fast forward, whatever you need to do. Okay, so the first one is a warm-up. It is going through the different types of functions and things that we've done up to this point. If you notice in Table A, it is going up by the same x value that y is, 0, 1, 2, 3, 4, all the way up to 25, right? And then the y values are changing. So we just need to identify how they're changing. I think you can see from this one that it is going up 7.5 if you were to add it, or it's times 4 if you were to multiply it, right? But 10 times 4 does not give you 17.5, so that kind of gives it away. It's going up 7.5 every time. Now that handwriting is obviously not very good. I apologize, but you guys get the point. So you're adding 7.5, adding 7.5, so 25 plus 7.5 is 32.5, so we put that there. Okay, but then the next one is the 25th term, which makes it a little bit more complicated because then you've got to figure out what that is. And, of course, you could list it all the way out if you want. I wasn't trying to do that. Get that back up there, sorry. Apparently it's going to close it all the way out with the new update, but whatever. So instead, let's think about how we could maybe write an equation to allow Desmos to do this for us. Well, first of all, we know that the x value when it's 0, that is our y-intercept. So this would be a y-intercept of 2.5, and it goes up 7.5. So if we were to write this in linear form, it is 7.5x plus 2.5, because that's what we started with. Okay, so now we can type that into Desmos. Do it as quickly as we can here. So we've got y equals 7.5, x plus 2.5. Hit that the gear icon, change that to a table, changes to 25, and that tells it it's 190 for that value there. Okay, for table B, all right, so this one, it goes 2.5 to 10 again, but then it goes 10 to 40, so that's clearly times 4, right? So we can multiply all the way up. 160 times 4 would be 320, 640. I know you guys could do that in your head as well. And then you've got the 25th term, which I have no idea off the top of my head. It's going to be a very massive number. So we're going to write this one as an exponential. Y equals, again, starts at 2.5 times whatever's happening, which we said is times 4 to the power of x. All right, so go ahead and type this one in. Y equals 2.5. parenthesis 4 to the power of x. Change that to a table. You can kind of see how it's that one's a horizontal or a diagonal line and one is that curved line, right? So we're gonna click the gear, change that to a table, scroll on down, hopefully, there we go. And that is a massive number. So 2.81475 times 10 to the 15th power. That means there are 15 spots after the 2. This is only 5 of them, so we could add in another 10 zeros. Okay? All right. So we've talked many a times about how that's going to work out, right? All right, let's go through an example. This is actually a really good one. My wife's mother my mother-in-law actually has a lake, and she has to deal with algae in it all the time. In order to control algae bloom in a lake, scientists introduced some treatment products. Once the treatment begins, the area covered by the algae in square yards is given by this equation. A equals 240 times 1/3 to the power of t, where time is measured in weeks. Okay, so what they're doing is they're killing off the algae. We would call this decay. This is what we're focusing on today, is exponential decay. All right, so in the equation, what does the 240 tell us about the algae? Well, let's come on back up. It says, the area covered by algae in square yards is A, right? So this must be the original area. It's the starting area covered by algae, which means the 1/3 Okay, that is our decay, or that's our decay factor. All right, which is what it's being multiplied by. So basically, every week, a third of that algae goes away. All right, so we're going to create a little graph here. So we're going to start at 240, and since it's 1/3, that tells us it's going to go down. So 240 should be all the way up here to the top. All right, and then we've got to figure out what's the best way to do this, right? Let's see. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Ooh, well, 240 divided by 12, let's see, would be, what, 20? So 20 a piece. I think we can go a little bit less than that. Let's go 15 a piece. So we're going to go 225. See if this works out. It might. Yeah, we'll try it. 210, 195, 180, that's not going to work. Maybe. 155, 140, 125, 110, 95, 80, what's that, 65, 50, probably messed up somewhere along the way, 35, we'll say that this is 20, so then you got 0 to 20, which is a little bit of a broken thing, but that's okay. All right, so what did we start with? We started with 240. There you go. That's at hour 0. Then we're only going up to 4, so let's just mark these periodically. 1, 2, 3, and 4. Okay, so after 1 week, it's going to be 1/3 of that, right? So 240 times 1/3. Well, let's think about this mathematically. Oh my gosh, my handwriting is so bad. I'm just kind of holding it up in the air here, but... Okay, so 1/3 of 240. Well, let's see. That would be, 240 is divisible. It's like 80, 80, and 80, right? So times 1/3 would have to be 80, because it's 80, 80, 80 plus 80 plus 80. So it'd have to be just 80. So 1/3 would have to be 80. Okay, so go to 1, go all the way down to 80. Turns out we took a long way down, but we didn't necessarily have to. Then we take 1/3 of 80. Okay, now that's not a nice pretty number. So we're going to calculate that, kind of estimate it here. So 80 times 1/3. Okay, 26.7, right? Or another way to think about this is to go ahead and write our equation, and then we can figure it out from there. So we've got y equals, it started at 240, then it's down 1/3, okay, to the power of, we'll just say x, right? And so then make your little gear, click your table, okay, and so you can see we go 240, 80, and about 27, we'll say. Okay, so 27 would be somewhere in here. Then we go to the third one. Click a 3, which will be about 8.9. And then 4, which is about 3. So 8.9 and 3. Oof. It's going to be like there and like there. Okay? All right. So then you graph it, right? Something like that, but it's obviously got to connect all those. Okay, it looks like that. Remember, it's not going to touch 0. And it says about how many square yards will the algae cover after 2.5 weeks. So 2.5 weeks is about there. I'm going to guess it's going to be about, let's say, about, I don't know, 17, 18 yards. Okay, that's my guess. But remember, since it's saying 2.5 weeks, we can go back to Desmos, plug in 2.5, and it's going to tell us how many, which is 15.4. So my guess was close, but if you want to be exact, so using Desmos, it's 15.4 yards. Okay? All right. So that's how you apply the table, also how you apply Desmos, right? You can type it in and kind of see where that is going to be. You could also, like, let's say you wanted to look and see how long until it gets to maybe like 155 square feet, right? What could you do for that? Well, I go to Desmos. Instead of looking at it that way, I would type in y equals 155, and then I look at my map, or excuse me, my graph, and see about where that crosses. Okay, so that's one way that you could find the y value there, is figure out how long it took. In this case, a little bit less than a half a week, right? Okay, continuing on. So, once a glow stick begins to glow, it can glow for hours. The graph shows the luminescence and lumens of a glow stick over time in hours. Scientists have found that the glow stick luminescence decreases exponentially. So how do they know that? How do you check that? Well, I'm going to show you, and this is on your quiz. So what you're going to do is look at the y values, okay? Now we can tell that it goes down by, what, 1.9 if you were to subtract, but that's not what we're trying to do because it's exponential. So we know it has to be multiplying or dividing, right? And so since it's going smaller, we know it's going to divide. So what you're going to do is you're going to take the second value and divide it by the first value, and that's going to give you your growth factor. So you're going to take y2 divided by y1, and that's going to give you your growth, or in this case, decay factor. Okay, so 4.4 divided by 6.3. Okay, we're going to plug that in our calculator. 4.4 divided by 6.3. Okay, and that tells us that it is 0.69841 and some change. All right, if I want to change it to a fraction, it's 44 over 63, so that doesn't help us at all. So just 0.698. Okay, so if this is a true decay, then I'm going to do it again, and I'm going to do these two this time. So 3.1 divided by 4.4, and I'm going to verify that that is the same number, right? Remember, we want to be consistent. So 3.1 divided by 4.4 is about 0.7045, and I know that's a little bit off, but we can see that it's kind of around. If you were to round it, it'd be 0.7, and this one would also be 0.7, and that's close enough for me. Okay, usually we want it to be exact, but this is really, really, really close, so we can tell that this is working. Okay. So how can you check if the graph supports the scientist's claim? Check for slope or growth / decay factor. I know you can hear my stylus, so I apologize. Not much I can do about that, unfortunately. Okay. How much less bright is a glow stick after the first hour? Okay, what it's asking is, what fraction of the original luminescence is that? It's saying it is 6.3 minus 4.4, which is 1.9, right? That's how much is left over, that luminescence. So it's saying how much of the original is that's left over? Well, 1.9 divided by 6.3, which is the original. So this is what's left. This is what the original is. And that tells you that theoretically, if it's taking away 70%, it should be about 30% left over. Right? So 0.3. Okay. So one thing I want you to take away from this, we haven't talked much about this, but there are two ways to write an exponential function. You could write it like this, like we did the other day, or you could write it like this. Okay, where the R is what we call the rate of change. And we'll talk more about this next week as well. But basically, that rate of change is how much it's going down by, right? So since we knew that it was going down 70% or 30%, excuse me, yeah, it's going down 1.9, right? 1.9 is 30%. So in this case, it would be 1 minus 0.30, which is 0.7. So if you're not really sure how to find our growth factor or decay factor, okay, you could always take the percentage of what was taken away and then subtract or add that to 1, and that's going to tell you your growth or decay factor. All right, we'll talk a little bit more about that later. Okay, let's bypass some of this other stuff. What fraction stays for each hour that passes? Bypass that. Complete the table to show the predicted luminescence 4 to 5 hours after. Right, so we know that this is going down 70%, or it's only 70% of the original. So this is times 0.7, times 0.7, times 0.7, right? So in our calculator, 3.1 times 0.7, which is 2.17. Or 2.2 if you want to, okay? And then 2.2 times 0.7, which is 1.54. So about 1.5, we'll just say, okay? Describe how you would find how many lumens the glow stick produces after 10 hours, right? You would end up using the formula that they talked about. So you start with 9 in this case, and then it goes down 0.3, so you put 0.7 to the power of h, I guess, right? So you'd use the formula that we've talked a bunch about. Okay, so this is getting pretty long. I think what I'm going to do is I'm going to upload this as 2 separate videos, because that's basically lesson 6.4, and we combine this to 6.4 and 6.5. So I'm going to post this video, and then I'm going to make another video for the 6.5 part, okay? All right, guys, look forward to that. See you soon.